Okay. All right. So sorry for turning off my camera. As I said, my internet is quite unreliable. I'm in a quarantine hotel, so there's nothing I can do about changing my internet. This is a project that I had with Mi Song Im, who was actually an undergrad at Georgia. And throughout our project, and actually throughout our time at IAS in that summer's collaborators program, we've also been talking to Arik and CJ for both postdocs at some point in their life at Georgia. So I think this is a very fitting situation for me to give a talk. So I'm mainly going to talk about Specht modules and two bases for the Specht modules. So these are irreducible modules for the symmetric groups. So classically, people have studied invariant theory for SL2 and SL3 using diagrammatics. So for SL2, this result by Romer-Tell and Weil says that the pictures, all such pictures on a unit disk where you draw non-crossing arcs for orientations. Each of such picture would give you an element in this tensor space where you take either V or V dual. So V here is our natural SL2 module, and V minus is the dual of that. And then this tensor product just means that any tensor factor can be either from V or V dual. Actually, depending on the orientation of the arrow at the boundary point, the plus or minus is uniquely determined by this picture. But there's a way of interpreting this picture as an element in this tensor space so that SL2 acts on that by 0. Actually, that's given by the evaluation co-evaluation map if you're an expert. And there's a similar story later developed by Kupperberg for SL3. So here, instead of having arcs, you have trivalent vertices. And there's some convention about the orientation, which we will mention later on. And here, boundary points are also labeled by either a plus or minus, corresponding to which tensor factor you should be taken from, which vector space should you take in this tensor product. And again, all such pictures, they would give you things on which SL3 acts invariantly. So this is classically known, but then this was generalized by Cautis-Kamnitzer-Morrison to a categorical context and for arbitrary SLN. So my project actually only relies on a combinatorial construction, and actually in relevant literature, you only see combinatorial definitions, but this is what's really hiding in the background, and I'm sure there are experts in link homologists on link homology. So I will make sure I mention this machinery hiding in the background, which actually motivates some of the results. So they constructed a diagrammatic category. So this category is linear over the vector space of the complex numbers adjoined with a variable. This means that the morphism sets are vector spaces over this field. So objects of this category are sequences of integers, and morphisms are given by vertical and horizontal stacking of the following generators. So for example, the first two, you would have trivalent vertices where the edges are labeled by positive integers. Here, the blue numbers are only positive, and they represent the thickness of the strands, or you can think of it as the number of strands being bunched together. So here I would have R plus S strands going up, which gets split into two thick strands, each with, with thickness R and S. So if you interpret it this way, the convention is that the number of edges coming in is always equal to the total number of edges going out, and vice versa in the other direction. And I view my morphism as going from the top to the bottom. So even in this case with opposite orientation, it's still going from the bottom, going from the bottom to the top. I said it the other way. Here, the source and target would depend on both of the thickness and also the orientation. So here, this boundary point would have an upward arrow, which means I go from a positive integer with that thickness, and then the monoidal structure is given by vertical concatenation. So here I go, sorry, well, here I just go to the tuple R comma S. And then if my boundary point has a downward arrow, that just means my source would be a negative integer. So it's also generated by pictures with tags where the orientation on either side is opposing each other, and the thickness would sum up to n. And you can generate the middle two pictures using the remaining four pictures, but I also want to put them here. And it's also subject to local relations on these diagrams, which I will omit. But I will mention two relations. One is that if you have an edge with thickness either 0 or n, then you just erase that part of the picture, but keeping the remaining part of the picture constant. However, if you have an edge which is labeled by an integer that's too big, so bigger than n, then the whole picture dies. You don't care what happens to the rest of the picture. So the main result of their paper in 2014 is that this gives a diagrammatic presentation of the category of modules for the quantum group SLN. So what that says is that there is a CQ linear monoidal functor from this web category to the category of modules. Now on the objects level, each positive integer gets sent to an exterior power of the natural module, and each negative integer gets sent to also the same exterior power, but of the dual. And when I say monoidal, I was hinting earlier, the horizontal stacking is giving me the monoidal structure. So, so a concatenation of two sequences of integers is given by tensor powers of the modules on the other side, tensor products of the modules. And a key result, I will tell you what it does on the morphism on the next slide, but a key result of their paper is that this functor is full on a subcategory. And you can already see that the image would be all the things that are tensor products of such modules of such form, or linear combination, well, direct sums of them. So it's full also at the level of morphisms. So if you want to look at all the module homomorphism between two such modules, then you can describe them using webs. Of course, to get a basis, it's a little more tricky, but at least you get a spanning of the webs. Okay, so just to mention the morphisms a little bit, you don't really need to know this, but for this map, which I call the merge, because you're merging two strands into a bigger one, you just take your two exterior product and then just put them side by side, and you can check it's well defined. And for the split map, you do the only thing you can do, so you take an exterior product and you have way too many of them, so you knock out a certain number of them, so you have the correct number of them left, which you put into the first tensor factor, and the stuff that you knocked out earlier, you shove them into the second tensor factor. So in total, collectively, you have enough tensors, but you're just putting them in the two tensor factors. And then you do this over all the positions that you can knock out the entries, so that this works. And you take the sum over all such combinations. And then they just checked that all the relations would hold. So, so this is just in case you're wondering what it does on the morphism, sort of agrees with the picture. So in the very last section of their paper, they also gave a diagrammatic way of computing the braiding. So this braid, this picture, represents a morphism in this category. So it goes from, because the the thickness gets swapped. So it goes from this tensor product to the one where you swap them. And this is defined by applying the universal R matrix on that 2 tensor factor. So it's the Casimir tensor element. And in the classical case, this is just the swap map. So because the webs, as we said earlier, they span the morphism set, so we should be able to write this morphism as a linear combination of things like the webs. And that's what they did. They gave this explicit formula of how to write that in terms of such ladders, but it's just one form of the webs with very explicit coefficients. So I didn't want to trouble you with memorizing this one because you don't need to remember them. But these are just, there are some powers of Q in the front, and the power of Q depends on this, the thickness that you take, and you sum over all the possible thicknesses where this picture makes sense. So it still goes from S tensor R to R tensor S. Okay. And this is the main motivation behind our project is you, yeah, we'll say more about this later. Okay. Now, for our project, when n equals 2 and n equals 3, in other words, in a case that's known classically, but we certainly want to also do it more in the more general setting. So we still need that SLN case maybe in the future. But in the n equals 2 case, the relation I did mention where you erase all the strands with thickness 0 or 2 and kill anything above tells you that the only allowed thickness, the one remaining, is the thickness 1 strands. So all the strands are the same. They're all single strands. And sometimes you would have, for example, here, like a thickness 2 down below, and you would erase that, but you get some sort of inconsistency in the orientation. So here you do have to fudge it a little bit to be consistent with the classical construction, where you interpret this as going the other way with -1 strands and do the computation mod 2. So if there's an expert in the audience, you can tell me if there's some way of interpreting this categorically, because somehow this is just combinatorially manipulate this orientation so that the orientation is consistent. I also want to mention that in the thesis of Scott Morrison, which is where a large part of this project was based on, his orientation originally was consistent with the classical construction. So for example, here when n equals 3, you would have 2 strands going up, which gets split into 2 single strands. But classically, this should be 3 strands all going out. So the strand, the orientation down below should be 1 going downward, which is again sort of equal to the original one mod 3 if you interpret the changing of orientation is the same as negating the thickness and do the computation mod 3. But in any case, there's something you need to do to make the orientation consistent with the classical construction. But in his thesis, you don't need to do this extra thing. It's actually already consistent. Right. Okay, so before I start defining everything, why did I mention the webs? Even though my object of interest would be the symmetric groups, well, if you take 2 modules for SL2, here I take the trivial module, and I also take the one that's tensor product of my natural module, so V is V plus here, and SL2 knows how to act on the tensor product. And if the second module happens to be a bimodule for both SL2 and the symmetric group, so these 2 actions, they commute with each other, then graduate level algebra will tell us that the home space between them would also be a module for the symmetric group, coming from the right module structure of the tensor product. And indeed, this is really just capturing all the things inside here on which SO2 acts trivially. So how many copies of trivial modules are inside here? And if you have such an element, which is the image of the trivial one, and once you rewind the definition, the action is really given by permuting the tensor factors in the classical case when Q goes to 1. Okay, so just in case I wasn't being clear, our project is only based on the case when Q equals 1. So, but I do want to do it in the quantum case, definitely, in the future. So, for example, this space of invariants from the theory of SLN webs, this would be spanned by all the pictures from the trivial one is the 0 or the empty exterior power. So I have nothing, no dots down at the bottom. And the top, I have 2D dots. So this is when D equals 3. D equals 4. 2D dots with which are labeled by plus because I have V. And then all such pictures I can make using my trivalent vertices and stacking them together. I just need to remember that every time I have a strand with thickness either 0 or 2, I erase that part of the picture. So in the end, I get a picture like this, which is a cup-like diagram. So all the cups would not cross each other. And then, of course, I need to sort out my orientation a little bit. But basically, I get a picture like this. So this is the motivation of why this cup diagrams, and by definition, these are non-crossing matchings of 2D dots on the top. So I just pair the dots with arcs, but the arcs cannot be allowed to cross each other. So these are the basic combinatorial tools we use to define Specht module in one construction. Okay, so my vector space corresponding to this partition D comma D would be the one with such a basis given by all such diagrams. And the action of the symmetric group is given by a case-by-case scenario. So when we do this construction, we forget all the SLN web machinery, even though we will start remembering it in a few slides. But in the literature, it's given by this combinatorially defined action. So if the I and I plus 1 vertices are on the same arc, then the action is just negating that element, that basis element. And if the two vertices are on different arcs, then I get the same picture back, plus the only other picture you can make, connecting these 4 vertices so that it's still non-crossing. And the 4 dots can be far away from each other. So these two have to be adjacent, but A and B could be anything else. As long as the part of the picture I'm not drawing here, the remaining part of the picture stayed the same throughout the 3 pictures. So these are the only thing that get changed. And a similar formula holds even though I and I plus 1 can be sort of the 2 right endpoints or the 2 left endpoints. You always get the same thing back, plus the only other picture you can draw where the arcs are not crossing. So I only wrote one more case, but there should be one more here where they're both left endpoints. And you still need to do some checking here, such as all the relations hold, but this also gives you a definition of the action. Okay. Classically, these Specht modules were constructed using things like Young tableau and Young diagrams. So I'll start with a Young diagram with this shape, and a Young tableau with entries from 1 up to 2D would be a filling of the boxes by these entries. So a general tableau does not have any restriction on the order of the entries, but if it's a standard one, then the entries must increase along each row and along each column. For each tableau, I can record the entries by writing down writing them down each column, and then from the leftmost column to the rightmost column. So here I get 6, 2, then 1, 10, all the way to the last column. There's a 9 missing here. And then I can define the descent of this column word by counting the number of pairs that are out of order. So for example, 6 appears before 2, that's out of order. I count that pair, and I just count how many pairs are there. So it's a measure of how much you're out of order. And then I'll define another module for the symmetric group by first forming a vector space over the complex numbers spanned by all the Young tableaux. So not just the standard ones, but all the Young tableaux, modulo some linear relations that I put on the Young tableau. And the action of the symmetric group is given by permuting the entries. And the non-trivial thing to check is that, so all the relations are satisfied, but also the claim is that this module I defined has a basis given by the standard Young tableau. So once you permute it, it's no longer standard, but you can still rewrite that element into standard basis using the linear relations. And this, I didn't write down the name. This basis is called the Polytabloid Basis. So these are the two bases I'm interested in, the web basis and the Polytabloid Basis. Right, and you can easily see that from the linear relations that it's irreducible. So you can generate, sorry, did I get cut out at some point? It says my internet is not stable.
Thank you, okay.
Can people still hear me? Okay, okay, cool. So yeah, just let me know if I if it sounds like I'm breaking off. Yeah, so you can generate all the elements, and you can see that pretty easily here. So one of the relations would imply that if I is underneath I plus 1, and that means if I take out the column word, I appears before I plus 1, and I act Si upon it, the linear relation would imply that if I swap them, then I get 2 polytabloids back. One is the original one, and the other is if I swap them. Okay. And the other one, if I take out the column word, now it's exactly 1 pair.
Sorry, I think you cut out.
Suitable simple transposition so that you get exactly 1 more descent, and then you keep going up the descents to generate all the polytabloids. And to keep track of this picture where you keep going up in the descent, Russell and Tymoczko, they invented this tableau graph so that you arrange your tableau in such a graph that each time you go down a row, the descent would increase. So I start with the top, the tableau with column word that's the smallest in that sense. So if I take out the column word, it has descent 0. Everything is in order. And then if I can act on it by a simple transposition, where the relative position of the entries is given by my last slide. So 4 appears before 5 in the column word. So I can act on it by S4. Then the new one would have 1 more descent. But I also want to keep track of this relationship by adding the simple transposition I used and record that on the edge. So this is more than just saying that has 1 more descent. I also write down the simple transposition. And then I keep everything on this tableau graph until I go to the one with largest descent. Okay. So in addition to comparing them by descent, I can also look at this tableau graph and define a new partial order that if 2 things are related by a path, so if I can go from one to the other by a directed path, then I say they're comparable in this partial order. So it's really a refinement of the descent. sometimes you might have two tableaux where one has a smaller descent than the other, but then there might not be a path from one to another. So, so this is now a partial order instead of a total order. Okay. So what's the key statement here? So their result is saying, the result is saying that the two constructions, they both give you the Specht module, and the irreducibles are parameterized by the conjugacy classes or the cycle types. So that's the partition we're looking at. And in general, the image of a polytabloid is not very nice. It's a linear combination of webs. But on this very specific one, the one with lowest descent, the image would be a single web with cups side by side. So this one, I'm writing down here. And a sanity check is to compare the dimension of the two modules. So these are actually two equivalent definitions of the Catalan number. And an explicit bijection is given as follows. So given a standard Young tableau, the corresponding web would be the one where you take out all the entries from the first column and use them as your left endpoint. So these 5 numbers colored purple here. And then the non-crossing condition would tell you there's only one way to draw the rest of the diagram. So for example, 7 has to go to 8, otherwise you'll be forced to have a crossing, and then you can complete the picture. This will be one of the 2 combinatorial bijection we're giving. So I will refer to this as the Catalan identification, where you use left endpoints and complete the picture. So the key thing here to note is that what you get is a non-crossing diagram. So I kept saying non-crossing because we will be seeing crossings later on. But let me just recap the result. So on the cup diagrams, you can compare the cup diagrams like this just by looking at their counterparts using this Catalan identification over at the tableau side, and then compare them over there using that tableau, that path thing, that refinement of the descent. So you can transfer this partial order over to the cup diagrams. And what Russell and Tymoczko did was they studied the combinatorics and they reached the conclusion that if you send a polytabloid over, so just to explain so I'm not writing any maps here. This should really be a map applied to the polytabloid, but because this is unique up to a scalar, so it's canonical in the sense. So that's why I'm just identifying them using equal signs. So the image of a polytabloid would be the corresponding web. So phi of t is the Catalan identification, the web, plus something, but the something could only be lower. So this is saying the change of coordinate matrix is unitriangular with ones down at the diagonal. And they also did a bunch more examples and conjectured that all the lower terms must have positive coefficient, and actually all the lower terms must occur. So maybe this is implied by the positivity here. You can never have something with 0 coefficient. So everybody who's lower must appear in this sum. Okay. So quickly after their paper, Rhodes also proved it last year that partially this conjecture is true in the sense that if you do show up, you have positive coefficient, but some of them might have 0 coefficient. Well, it's actually this is true, but this result only implies that the coefficients are non-negative. And let me just quickly talk about the proof a little bit. So he's actually giving a third construction of the Specht module by looking at a matrix with 2 rows and 2D columns. And he's looking at a space who's spanned by products of minors of this matrix of the form down below. So for each cup diagram, he associates to that diagram a product of minors where you take out the columns associated to each arc. So for example, this arc joins the first and sixth column, and you take out those two columns to form your minor, and you do it for all the other arcs. And you look at all the space spanned by such minors, like in terms of polynomials. So you have entries represented by variables, and then you look at a polynomial, and then look at the span of those polynomials. And the action is given by permuting the columns, and that induces an action on this space. And he used the Plicker relations among this Plicker coordinates. So so there's a relation that says if you take out the 4 columns and form them, group them into these 2 subsets, you can rearrange them and get a sum of the other 2 ways. And essentially, this is how he established that this construction is equivalent to the other 2, because essentially this is the same as the Garnier relation. The linear relations I was not telling you about, but this is really just a recap of that relation in terms of the minors. So what we're proposing here is we should really interpret this diagrammatically. And there are 2 benefits. Of course, it's a lot easier to remember these relations this way, but also we do get a crossing, which we can interpret as the braiding in this category, the braiding that I was telling you about in the very beginning. But here I just want to explain the combinatorics, the correspondence. So when you take out, just as I was saying, when you take out 2 columns and form a minor, that corresponds to an arc which joins those two indices. And that actually corresponds to a column in a tableau. And everything is color-coded, and things work out the same way on the right-hand side as well. The only thing is that here we're allowed a crossing. Okay, so once you have that in mind, now we're dealing with webs which might have potential crossings on the top. And I want to interpret that as the action of the symmetric group. So once I allow crossings, my action of the simple transposition is putting a cross on the top on that suitable position. And a reformulation of my action is that if you put a crossing on a single cup, that just gives you a negative sign. And if the 2 dots belong to different arcs, then I have a single picture like that, which I can to 2 webs to match with my original definition. So my definition is now defined as this, but then I add in a new relation, such as follows, which is the one I'm proposing here. And the fact that all the 3 things are essentially the same thing corresponds to the fact that 3 constructions are equivalent, and why Rhodes' proof would work. Okay. Here is just to say that in the classical case, I don't care about under versus over crossings. Everything would be the same. Okay, so I just have a cross here. So now I can explain Rhodes' proof to you in a very quick way. So I already know that the T0, the lowest polytabloid, corresponds to this web down at the bottom. And to act on it by a word is to put a braid on the top, while braid where undercrossing is the same as overcrossing. And then one powerful thing about Rhodes' result is that this relation works globally in the sense that even if my arc intersects with other arcs and creates more crossings, I don't really care. I just care what vertices are connected together. So if A and C are connected together, I don't care if I stretch this arc long enough and somehow intersect other arcs. As long as they are connected together, that's the same picture in my view. So this relation sort of works globally, even if I might be messing up with the rest of the picture. So his result is saying once you have, well, we formulated his result in a way that says, once you have such a picture, you can shake it up so that you can manipulate the strands. And whenever you have crossings, you just resolve them. But notice that you only have positive coefficients here. So that's how he got the partially positivity result, which says if you get something, it must appear with positive coefficient. However, his result doesn't say what terms show up. Like you can't guarantee that you can get all the lower ones. Okay. I wasn't sure if there's any link homologists in the audience, but I want to point out that this crossing is really the braiding in the sense of web category. So if you zoom into this red box, I'm really using the relation that a crossing is either the identity or the term back. Here I'm specializing Q equals 1. Now, this is the original picture from the Cautis-Kamnitzer-Morrison paper. We just need to remember that the middle edge here is labeled by 2, so that has to be erased, and that recovers the classical picture above. Also, just in case there are link homologists in the audience, the reason we did not take this approach is because, one, there's orientation issues here, as I was mentioning. Another thing is if you really want to use the webs, you have to apply this locally. So the freedom I mentioned earlier, that if I somehow pull the strands down, far down and create some crossings with other strands, as a link homologist, I would have to care that new crossing that I created. So I have to make arguments about Reidemeister moves. And if somehow I created a new connected component, which is -2, then I would get a negative sign. And somehow Rhodes' argument is this thing is actually the key in this project and also in higher SLN cases, is you want to somehow be able to get away with saying that never happens, or if that happens, it happens across the tables, so you don't you can never happens a priori because they know the unitriangularity result. Yes.
Sorry, we didn't hear what you said.
Oh, I was getting excited about the circle relation because I think that's the key in Rhodes' proof, is that his argument bypasses this case. So he can somehow argue that, well, he didn't mention this explicitly, but his construction sort of is saying you can avoid looking at this relation. Or if you want to apply this relation, his method sort of tells you that negative sign has to apply to every term across the table, which in the end doesn't happen because you have the unitriangularity result. So in some sense, his proof really worked because he had a way of dealing with this relation and saying that this doesn't apply to some of the terms, but yeah, anyway, well, I think I'm saying too much on this. So let's actually talk about our proof. I think I'm running short on time. So yeah, if you believe that the 3 relations are all the same, then you can probably believe that the correspondence I give here that assigns to a tableau the web which joins the arcs in the way I described. So if 1 and 3 are in the same column, then I connect them by an arc. Same for 2 and 6. Then for each tableau, I can get such a web. And the fact that all the relations are the same is telling me that this is a module homomorphism. So I've just given you the image for polytabloid. The only thing is that the image is not nice in the sense that it has crossings. And this is the second identification I'll make. And this is what I call the column identification, opposed to the earlier, the Catalan identification, where the thing I get is non-crossing. And I use the left endpoints. Yeah, so once I have this image, then I just need to express it in terms of non-crossing cup diagrams. And to do that, I just need to get rid of all the crossings, and I form this crossing resolving graph by the following. So each time I see a crossing, I apply my relations. My relation here, oops, to get rid of that crossing. So I get two terms. One I get from interchanging the two right endpoints, 3 and 6. The other I get from interchanging the two inner points, 2 and 3. And I keep doing this until I have no crossings anymore. At the end of the day, I would have a bunch of non-crossing diagrams as sinks as in this graph. And sometimes I would have repetitions, but that's okay. That just tells me how many times, what are the coefficient in front of this diagram. So that's counted by the number of paths. And the existence of a certain term is the same as having a path from the top to that diagram. And even though the graph does depend on the choice of the crossings at each stage. So here I could have decided to resolve that crossing instead, but for existence, you just need to come up with one sequence of crossings to resolve. Yeah, so here's our reformulation. So of the positivity conjecture. So originally, they want to say that if two tableaux are comparable, then the corresponding web should appear in the expansion of the other. The corresponding web for one appears in the corresponding expansion of the other over in the world of webs. But now that we give the explicit image of that tableau in terms of webs, so W1 is the one on the top, and then W2 is the one down at the bottom as a sink where you want to argue it somehow shows up in this graph. So let me quickly give you one more example before moving on to the more general case. Any questions at this point? All right, so here are two tableaux which satisfy the premise of our proposition. So these two are comparable because you can get from one to the other by applying S5. So if you do S5, you get to this. And the image of this polytabloid would be the one downstairs. So 1 and 3 are joined together, 2 and 6, and so on. For this one, you use 1, 2, 4, 6 as your left endpoints. So this is the one on the top. And I want to argue you can manipulate the strands to get from one to another, okay? And you can do it by the following. So first I guess you can already see this. So you interchange 5 and 6, and then you interchange 7 and 8. Now, these two pictures still don't look the same, but they now at least have one arc that agrees. And our key argument is to make inductions on that. So once you have one arc that you've moved to the desired spot, you can delete it because it doesn't interfere with the rest of the pictures anymore. And now you can keep doing this. So that's basically the argument we're using here. And basically, yeah, so that's our main result, is to prove the positivity conjecture. So now we've proved that all the lower terms must show up in addition to having non-negative coefficients. Because we have that identification, we can also talk about the inverse map. So given a web, I can also use the column identification to figure out what's the image on the other side. So now I just put 1 and 8 on the same column, 2 and 5, and so on. And a similar thing also happens here. So before we started with a standard tableau and get something with crossings. Here we started with something without crossings and get a non-standard. So in any case, one of them is nice and the other is not nice. Here, the image is not nice. It's non-standard, but we can expand it into a linear combination of the standard ones using the Garnier relations. And we also gave a conjecture which says when you do that, the coefficients are either 0 or plus or minus 1. So not all the lower tableau would show up. The ones that do show up have plus or minus 1 coefficients. So Arik was actually telling me something about this. He said, if you use geometry, if you use cohomology group of Springer fibers, you'll see this very easily. So that's the story that I want to learn about next. So enough about SL2. I still have 10 minutes to tell you more about SL3. So for SL3, as I was hinting earlier, the convention classically was that all the edges must be going either all in or all out for each trivalent vertex with additional cups or caps as generators. And we do have relations. Just like SL2, we really have a relation that says a circle value is 3 for SL3, and then a bygone is -2, and this is exactly the one that's going to give us trouble, that could give us negative coefficients in expansion. And then if you have a square, a foregone, then you can delete the opposing edges in 2 different ways and take the sum. So just as before, I can form the space of invariants that gives me a module for the symmetric group. And the action is putting a braid or a crossing on the top. Now, the relation for SL3 is the following. And now you do need to keep track of the orientation. Okay. So the result by Peterson, Pilyavsky, and Rhodes, which we also proved independently by us, is that this construction gives you the Specht module for this partition. So everything still works in the case of SL3 webs. The difference and the reason we proved it again is because in their construction, everything is combinatorics. So for them, these are not morphisms in a certain category. These are just arbitrary combinatorial rule you can use, and the crossing is not the braiding in this symmetric monoidal category. And so in that respect, you have a lot of things to check, even things like, checking all the relations. But for us, the compositions, the morphisms behave nicely with respect to composition. That alone tells you that you don't have to check the relations, for example, one thing. And then they have to actually do some counting regarding the dimension and other various things. So that's a very technical proof. And I just want to mention our proof a little bit, well, because it's not new, but to give you an idea of how to add the representation theoretical context to the story. So right. So basically, yeah, and I should say both of our results says that the polytabloid with the least descent goes to, again, the web with forks side by side. So analogous to the SL2 result. So the main idea is that you use a third basis of the Specht module, which is the Galvanizing basis. So this is a basis on which the uses Murphy elements act by scalars. And the uses Murphy elements, they generate the maximal abelian subgroup, subalgebra of the group algebra. And then in general, the 3 bases, they don't agree, but they do agree on this one thing. So in the SL2, these 2 things are identified under the module isomorphism. And in fact, you can compute the uses Murphy elements acting on both of them in the SL3 case, and you can compute the scalars. And the nice thing about the Galvan-Zeppelin basis is that the scalars, they help you recover the partition. So we computed the scalars, we recover the partition, that's the partition we want. So we know there's a copy of the Specht module inside, my space of invariants, but then we compare the dimensions to see this is actually all of that Specht module that we want. So the dimension argument comes from counting path in a Bertelli graph with vertices which are partitions, and then that's the same as the number of standard down tableau. So that's a pretty standard argument here. So our proof is basically 2 pages, and that's mostly diagrammatic computation, which is not very hard on this web. So that's where our result ends. We really would like to know some positivity result for SO3 webs. And we do have some groundwork that's already set up for us. So one thing is, what's the bijection between the 3-row tableau versus the webs? And people have given various ways you can do this. There's inexplicit growth algorithm given by Kuperberg and Kovanov in their original paper. But that's sort of an algorithm that tells you can propagate from the boundary to the rest of the webs. It doesn't tell you what the web looks like all at once. And then Tymoczko also gave you another bijection, which tells you what the web looks like immediately. But still, you might need to do some reductions using the relations. And then there are further results, by Russell and Tymoczko on arXiv last summer, is that you can use, again, the partial order from the tableau and transfer that to the webs. And they prove a similar unitriangularity result. And still, what's missing is the positivity result. So that's the one we really want to deal with. And also, for all these cases, the quantum case, and then for all the other SLN. So for the next 3 slides, I want to give you some of my ideas of how to maybe tackle this problem, and also to illustrate how much harder it is for SL3 and beyond compared to SL2. So again, that's my the scaling relation for the braiding. Here, I do want to remember it's over or crossing, over or under, even though I'm still specializing Q to be 1. And the middle edge, which is of thickness 2, I want to write it as double edge to remember that as thickness 2. And actually, this is how you see SO3 is not that much, well, the other SLN is not that much harder from not that much harder than SO3, because SO2 is different because you erase that edge in the middle. But for SO3 and beyond, you get the same picture. And then that computation I did by putting a braid on the top and resolve, I could have done that with the braid itself. So really, I'm expanding the braid. Here, I took the longest element in S3 and expanded using the scaling relation. And this computation, it looks really, so I'm not an expert in this, but these pictures are what people usually use for the Bott-Samuelson basis. And in this case, they're also what people use, I understand, for the Cautis-Kamnitzer-Morrison basis. And sometimes they don't agree. Like, for example, if you take this term from all the 3 crossings, you get something which you can further reduce. So this is a Bott-Samuelson basis element, which is not the Cautis-Kamnitzer-Morrison basis element. The Cautis-Kamnitzer-Morrison is the largest summand of this in this diagrammatical sense, which I'm still trying to understand. But what I'm really hoping to understand is how to compute these coefficients without doing diagrammatics, but interpret them as some sort of linear combination of the inverse Cauchy-Kamnitzer polynomials. And as you can already see, I'm not an expert in this, but assuming I know these coefficients in front of the Cauchy-Kamnitzer basis, I want to somehow use them as an intermediate between my standard basis and my web basis. And there's one last thing which I don't know how to interpret nicely. And this would be a universal computation, because in the end, I just put a bunch of forks down at the bottom. So the n would determine how many fingers each clause would have. So for n beyond, I just have more fingers, but the major part of the computation would be similar. So that's why I think it's, for SLN is not that much harder than SL3. The only reduction I need to make is gonna happen at the bottom here. And this is just one more computation for the longest word in S4, and I have a bunch of webs I don't know how to interpret. But I do want to understand how do they relate to the Cauchy logistic polynomials. But so yeah, that's the end of my talk. And yeah, thank you for the opportunity.
Any questions? So, I don't know. Jieru, can you hear me?
Very faintly, yeah.
Okay, maybe you can. So, how difficult is it to extend this to two arbitrary roles? Because I think you only did the two equal roles. Is that right?
So yes. So yeah. So I think yeah. So that is when you have a bunch of, so when you have uneven rows, that's when you do have some boundary points at the bottom. So I'm thinking about, say, SL2. Then you're not going from nothingness to dots. You're going from fewer dots to more dots, which means you actually I think I said something wrong, but I think, yeah, I'm torn between saying either you have a temporally leap diagram with a bunch of dots on the bottom, but I'm also tempted to say that you have just cups, but with a bunch of vertical strands. And I'm not sure which one is the right answer.
Okay.
If you require that the bottom dots, so I think it's just cups with a bunch of vertical strands, because somehow you have this this junction property where you can move the modules to the other side in the home, but adding a dual. So either you can do home from the trivial to V tensor 2D, or you can move some of the V's from the second entry to the first entry, but put a minus on the top, putting a dual. So I think that says if you have some bottom dots, they must have negative, the orientation must, they have like negative labels, which means the orientation have to go away from this boundary points. So I think that tells you must have vertical strands. You're not supposed to have caps between the bottom points.
Okay, I see.
Anyway.
Yeah, that makes sense. Okay, but you haven't really looked into this yet, because I mean.
No. So
modules for I don't know, these two rows for which you have two unequal rows as well.
yeah.
Okay.
You're right. Yeah, that would be the next immediate.
Okay, I see. Good.
Yeah. Yeah, so that'll be interesting to work out. Yeah. And in some sense, yeah. And in some sense, if you can do that, then you've done all the cases for the Specht module, because those are the ones you can cover from SL2 modules. For SL2 modules, you can have partitions at most 2 parts. So I think that's all the cases you can do.
Yes.
Yeah,
so
but that's,
this is why, yeah, exactly. So that's why I'm interested in this, because then you have the complete full picture.
Yes.
Okay, great.
Yes. Yeah. No, I'd be happy to talk more on that.
Okay, let's thank the speaker again.